Okay, so several students had some questions about problem 9.38 in the homework 3, the last one, the bridge rectifier. So I was going to go over in class, but then several other students also had questions about pre-labs that need to be submitted for this week. So for the homework, I might either create a PDF and post it online, or I might create a video and post it online, either ways. But right now the priority is completing the rectifier and then do the introduction for the Zener diode. So I'm going to go into that right now. Okay. Let's see. Share in OneNote. Oh. Chapter 5, I believe we stopped right here. Wave bridge rectifier. Okay, so the output of a rectifier circuit is still not quite a flat line, right? Especially if it's a half-wave rectifier. We only have half peaks. So in this waveform diagram right here, we can see the output of the voltage for a half-wave rectifier. Okay. So if you want to create a DC, we attach a capacitor to the output after the rectifier. So if this is the output from the rectifier, we apply it as input to a filter capacitor. And this is a load resistor RL. This is the capacitor. The capacitor, as you may recall from chapters 3 and 4 of EE201, are energy storage devices. Okay, they are passive devices, but they can store energy. So they receive energy from the circuit, they store it, and they release it back into the circuit at a later point in time. Now, depending on the size of the capacitor and the circuit variables, the capacitor can store a large amount of energy and can charge really fast, or it could store a small amount of energy and charge or discharge very slowly. An analogy can be made with a bucket of water. How fast or slow the water can be filled or released from the bucket depends on the size of the bucket, right? The quantity of energy that's coming in. Also, the fluid flow coming from the pipe, right? Basically, that would be the voltage and the current that's coming from the source. So a capacitor can receive that energy, store it, and release it back into the circuit. So if that is the output coming from the rectifier, and we can illustrate that with this peak right here. That's the diode output, goes into the capacitor. When it's in the positive direction, the capacitor is receiving the energy. We say the capacitor is being charged. So here the capacitor is being charged. Now, when the diode voltage starts dropping, meaning here, this portion, diode voltage is dropping. That means capacitor is discharging, right? And if we take a look only at one cycle, meaning 1/2 cycle, the capacitor would discharge all the way to 0. VC would be equal to 0 volts at some point in the future. But before it can release all of its energy, actually even long before it can release even like 10% of its energy, the next positive cycle arrives and begins charging again. So capacitor is releasing here the energy back into the circuit when the diode is off. But before it can discharge even less than 10% of its energy, the next charging cycle arrives and capacitor begins charging again. And so then the cycle continues. In the positive half cycle, when the diode is on, capacitor receives the energy, it charges up, reaches full load, diode turns off, capacitor is not receiving any more charge, it is now releasing the energy back into the circuit. Since the diode is reverse bias, all of that energy is going to go to that load resistor. So the output of the capacitor is going to the load resistor. Okay. And because the output of the capacitor looks like a ripple surface of the ocean, ripples or waves, we call this as a electrical ripple. Charges, then discharges, charges, and then discharges. The actual waveform, of course, now has a higher level than the previous output from the rectifier circuit. So this is known as the ripple or the ripple voltage, and typically it's on the order of millivolts. And if this entire portion can be called as DC. Okay. From two half peaks, we now have filled everything up. If you take the area under the curve, there's entire energy is coming from the diodes plus the capacitor. In the bottom half, of course, we see the current waveforms. This is solely the diode current. It's only on for a certain period of time. But then the output load current is right here. And we can see that it is nearly a constant level. Not quite flat, but far more than what was coming from the diode rectifier circuit. Make sense? And because it is filtering out our output or filtering out the ripple voltages, it is known as a filter capacitor. A filter capacitor. Typical values of capacitors that I've seen in our, in cheap adapters is about 1,000 microfarad or even 10,000 microfarads. 10,000 microfarads would be a capacitor that's about this big. Size of my finger, probably about the top portion. Okay. So 10,000 microfarads, about 100 millifarads. And that's a big enough capacitor size. Again, if we use smaller capacitors, and we can perform this experiment in the lab, smaller capacitors will only store a small amount of energy. So, and they will discharge very quickly. So the ripple voltage will be far larger. Okay. The bigger the capacitor, the larger the energy that is stored, the larger the amount of the energy that is stored, and the longer it will take to discharge or let go. And of course, there's trade-offs, as you recall from transient analysis. A couple of equations we can use to design a power supply. VR is the ripple voltage or the peak-to-peak ripple voltage. Typically, it's the order of millivolts. If you want to keep VR small, capacitor value must be higher. Inversely proportional, right? The bigger the size of the capacitor, the more energy it can store, and the slower it would discharge. IL is the load current, and T is the time period for standard power supplies plugged into the wall outlet. That would be 60 hertz, 60 cycles per second. Our time period would be 1/60. So in the lab, we would perform an experiment with a bridge rectifier circuit. And then the output, you can connect a capacitor to observe how it's being filtered out. Okay. Now, the output of the filter capacitor is still not quite a completely flat line, right? There's still this minor ripple, and I'm exaggerating the difference here. If you have 10 volts DC and you have like a 100 millivolt ripple in there, That's still less than, I don't know, 1%. And yeah, right? So very, very small, but it's still there. So depending on our application, which like all modern electronic devices, of course, require very strict flat lines, this is still not quite what we need. And so we must regulate the output voltage so that we have a flat line at the output. So here you would have a filtered DC output with a ripple, and we'd feed it into a regulator circuit, and the output of the regulator circuit would be a flat line it'd be something like this. And that would indicate it's a DC signal. V out level, voltage. Okay. And by far, the most common and the cheapest and the most effective device to do that is a Zener diode. Regulator circuits, again, depending on the application, especially like say modern devices like your charger adapters or your smartphones, smart devices, laptops, computers, those require very well designed regulator circuits. The simplest one of those is a Zener diode. Just by itself can function as a regulator. Okay. So here is the symbol for a Zener diode. It operates exclusively in the reverse bias. The cathode is still a flat line, but it now has whiskers. Still the cathode. This is still the anode. Okay. And I'll explain why it works in reverse bias. So let's go to the next slide for now. So this is the forward active region for a diode. Normal diode characteristics. Right? Normal diode characteristic. In the forward bias, diode will turn on after a certain point. For silicon, it's about 0.6 or 0.7 volts. 0.6 to 0.7 volts. Right? In the reverse bias, the diode is off. There is almost no current flowing through the diode, except for a small reverse saturation current, which flows due to the minority carriers that are present in the diode. Right? The minority carriers cross over the junction because of the applied reverse bias. If this is our PN junction diode, this is the depletion region. We have an excess of electrons here, an excess of holes here. This depletion region is devoid of charge carriers, except for minority carriers that are able to cross over the junction, right? So if you apply reverse bias, meaning negative here and positive here, what happens? The electrons and the holes are attracted by the voltage polarity of the external supply. So they are pulling away from the junction. Depletion region with increases. No current can flow through. But we also have minority carriers present in the devices. The minority carriers here are the holes. What happens to them? They are pushed towards the junction. When they're pushed towards the junction, they're able to cross over and a reverse saturation current results. That is noted by IS. This is very, very small, typically nanoamps 2 picoamps, very, very small. But as the voltage supply, the external voltage supply increases, more and more charge carriers are created. There are two mechanisms that occur. Okay, one is known as the Zener, the other one is known as the avalanche. Okay, so in the reverse bias, you would say typically there is zero current flowing through until it breaks down. So as we keep on increasing the voltage supply from the external voltage source, the junction would break down, and the breakdown occurs due to two mechanisms. One is Zener, the other one is avalanche. The Zener breakdown occurs because of heavily doped P and N-type materials. So if there's an excess of charge carriers in the P and N-type material, they acquire enough sufficient energy that they're able to cross over the depletion region in the reverse bias. So that is Zener breakdown. Again, Zener breakdown occurs is due to heavily doped semiconductor devices. So heavily doped P and N-type material that results in an excess of carriers being available. And this typically occurs less than 6 volts. And the second mechanism, or the second type of breakdown, is known as avalanche breakdown. And this occurs due to a process known as impact ionization. Impact ionization. This typically occurs when voltage is larger than 6 volts. And what happens there is that because of the external energy that is being applied by the voltage source Vs, the charge carriers acquire enough energy that they are scattering and moving around the lattice. Okay, when they move, they're moving in a random path. They will collide with other atoms. When they collide with other atoms, they're going to create more free charge carriers. They will dislodge electrons from the orbits, and those electrons are now free to move around too. So one electron can collide into another one, dislodging it from its spot, creating further charge carriers. Those electrons will collide with other atoms, creating more ionized atoms and more free charge carriers, thus creating a cascading effect. One results in two results in four, which results in 8, 16, 32, so on and so forth. And then there is no stopping that process. As long as Vs is present in the reverse bias, that process will keep going on until a breakdown occurs in the junction, charge carriers cross over, and a heavy current starts flowing through the junction. From that point on, the current that flows through the device or through the junction is almost independent of the external voltage that is being applied. The voltage across the junction remains constant, which is noted by this almost vertical line right here, but the current increases heavily. The small increase in voltage results in a large flow of current. So heavy current flow results, voltage is almost constant. And that property allows us to use the Zener diode as a regulator. And I'll explain that in the next circuit. But the avalanche breakdown is a result of impacts, collisions. It creates more ionized atoms. Hence, the process is known as impact ionization. It's a cascading effect like an avalanche, and hence it is known as an avalanche breakdown. These two mechanisms are separate and distinct. However, in general terms, nowadays, well, actually for a long time, any reverse breakdown that occurs is always referred to as a Zener breakdown. Technically, It could be Zener as well as avalanche, two separate mechanisms. But in general, all reverse bias voltages or all reverse breakdowns are now referred to as Zener breakdowns. Okay. So if you read Zener and reverse bias, it could be referring to both processes. And so we can create a model for the Zener diode in both the forward bias and the reverse bias. In the forward bias, it behaves like a normal or regular diode. Okay. A practical diode will have some diode resistance, and it also requires certain voltage for it to turn on. 0.6 to 0.7 volts for silicon, right? And so that is illustrated by this battery or voltage source right there. In the reverse bias, again, this is the ideal diode. It'll have Zener resistance plus the voltage that it requires to break down. And that is the Zener voltage. Note the polarity of the Zener voltage. Okay. A diode voltage is always measured as plus at the anode, minus at the cathode. That's your VD. Zener voltage is always measured. Zener is always operated in the reverse bias. So Zener voltage is opposite of the diode voltage. And same thing with Zener current. IZ will always be opposite of the diode current ID. Okay, because the references are always anode positive, cathode negative, but Zener diode is used in the reverse bias. So there's only a couple of minutes left. I'm going to quickly go through the Zener diode regulator circuit, but if you have to leave, feel free to leave. This is how we would use a Zener diode as a regulator. We would simply connect it in parallel with our load resistor, RL. Note the polarity for the diode. VD is minus at the top, plus at the bottom, because anode is at the bottom. But the Zener diode voltage, VZ, will be equal to VO. VZ would be equal to VO, which would be equal to minus VD. Okay. Right now, this is being used just for explanation purposes. Going forward, VZ will always be referred to as positive. Okay. The voltage magnitude is the same, except we're just referring to two different terms. That's all. So the way it would work is you have VSS, supply voltage. For VSS less than VZ, Zener diode is off, does not turn on. So whatever you give at the input, you obtain at the output. Assuming everything is ideal. But when VSS is larger than VZ, diode turns on. I should have inserted this here. Diode is off in the reverse bias, and V out is equal to VSS, and here V out is equal to VZ. So we have V in. Notice that there is a series current limiting resistor here. Otherwise, the circuit would not work. We have the Zener and we have RL in parallel. So the voltage is the same because they're in parallel. If V in increases, what happens to the current? Supply voltage increases, so supply current also increases, right? If supply current increases and there is no Zener diode, what happens to the load current? The load voltage and the load current would increase, right? Now you plug in a Zener diode in parallel to the load. What happens? Supply voltage increases, supply current increases, but the Zener diode keeps the voltage across the load constant. So if the voltage across the load is constant, the current through the load is also constant. Where does the extra current go? It goes through the Zener diode. Yes. It will. So that's part of the design that we'll look at. The question being asked is, what purpose does R serve, and whether it drops voltage across it or not. The answer is yes, it does drop voltage across it. So we designed it in such a way that the value is small enough. I mean, the value is large enough to minimize current loading, and it's small enough so that it does not drop a large amount of voltage. Question being asked, if its VS is 6 volts and VZ is also 6 volts, the answer is no, it would not turn on because the minimum the resistor will drop some voltage. So the series resistor must be small enough that it does not drop a large voltage. So there's a minimum limit for your supply voltage in order to turn the Zener diode on. And then there's a maximum limit beyond which a Zener diode cannot handle much current. So again, supply voltage increases, current increases. Zener diode turns on, it sinks the extra current through itself. It sinks the extra current through itself while keeping the voltage across it constant. And the maximum current it can handle is given by the power rating PZ. So in your pre-labs, you have a power rating for the Zener diode and you have the voltage. You determine the maximum current that it can handle. Then there's a couple of steps that you can do for the design. The pre-lab has a write-up at the beginning of the lab and has equations. So please go through those. Those are very helpful. There's also pre-lab videos that are available. So it's at least there for my section. I posted them on there, and you can take a look at those videos and reach out if you have further questions. Okay. We'll have to end class here today. It's 2:03, so we've gone over. But again, please reach out if you have any other questions.